let me open this. Cool. To do this, you're gonna have to understand, we have done this before, but it's okay. It doesn't hurt to review 3 different rules, okay? These are called exponent laws, I guess you can call this. There's 3 of them. The first one is this, it's the addition. If you have x to the power of a, let me flip this actually. If you have something like a to the power of x times a to the power of y, you're gonna have to add the exponents like that. An example would be something like 2 to the power of 3 times 2 to the power of 2. What is this equals to?
2 to the power of 5.
Right, that's the first rule. Second rule is very similar, right? Instead of it being multiplied, you divide, and then you would subtract them. For example, if it's 2, 3 over 2, 1, that'll be 2 squared, yeah? Just subtract the exponent. Third one is the double powers. So for example, if you have a to the power of x to the power of y, you want to multiply them. So for example, if you have 2 to the power of 3 to the power of 2, what is this equals to?
2 to the power of 6.
Right, 2 to the power of 6, not 2 to the power of 5, okay? Because that's this rule, not 2 to the power of 5, 2 to the power of 6. That is literally it. That's all you need to know for this. There's a neat little trick though when it comes to fractions. If you have a over b to the power of negative x, what you can do is you can flip it upside down and the exponent becomes a positive, right? And then if you want to toss something in the denominator, the sign will flip. For example, a to the power of 1 becomes 1 over a to the power minus 1. A to the power minus 5 becomes 1 over a to the power 5, like that. If you have x over y, you can rewrite this as y to the negative 1, toss y upstairs, bring the x down to the denominator, make sure to flip the sign. If there's no exponent, there is an invisible exponent of 1. Okay?
Okay.
Easy enough? Here, let me throw you into the deep end. All right, let's do this. Let's start with A. Step 1. If you can, before even putting the numbers in, clean it up if possible, like simplify it before, because we're first gonna simplify these guys, and then we're gonna chuck the numbers in. Look at A. Is that simplifiable? Can we do anything with that? What do you think? Can you open those brackets? It's a yes or no question, right? You have 50% chance of getting it right if you just guess.
No.
So you're gonna go with no, that's right, yeah. You can't open this bracket because you don't know how big this is. Yeah? Okay, let me see if I can do this right here. Let's go off on a tangent. You can only open the brackets if it has a number here, right? Like something like 2 or 3 or 4. This one is pretty simple. If you open this bracket, you just do a plus b times a plus b, and then you want to FOIL this and add up the like terms. You get a squared plus 2ab plus b squared. Anyways, we're talking about how to open a bracket, right? You can only open a bracket if this number up here, yeah, is a whole number. In fact, if it's something like this, you can't do anything with this. And especially if there's a letter or something, a variable, you can't do anything with that. But here's something a little bit more interesting. Power 2 is easy, right? Opening a bracket, you just FOIL it, you add up the like terms. What about something like this? A to the power, a plus b to the power 3. Well, the idea is the same, right? But it's just more manual work. Like that, and then you can keep going a plus b to the power of 4. You just keep multiplying it 4 times. But what if I told you because mathematicians, they're usually lazy, right? No one's doing this like 4 times. Not lazy, I like to use the word lazy, but it's the better term is efficient. We want to save time. No one has time to do this 4 times, or better yet, something like this, a plus b to the power of 100. What is that? And there's a better way to open this. First, understand, you see the power up here?
Mm-hmm.
The number of terms when you open this bracket is always going to be that power plus 1. For example, if its power is 2, the number of terms is going to be 3. Power is 3, the number of terms is going to be 4, okay? We're going to introduce a new concept here, which is kind of cool. So to open higher degree powers, you need to use something called Pascal's triangle. Okay, Pascal's triangle. And how do you build this? We're going to build a triangle, but it's going to be filled with numbers. To start off with, there's going to be a 1 on the peak up there. Okay?
Mm-hmm.
And then we're going to have 1 and 1 here as well. Okay?
Uh-huh.
These are ones. I know it looks like I. And then the fun starts from the third line. Every line has a 1 start and a 1 end, okay? But the
Mm-hmm.
middle guy, what you need to do is you need to like add up these two. So the middle guy is gonna have a 2 there. Okay? What does this represent? The first one represents something plus something to the power of 0. So a plus b to the power of 0 is a 1. The next line represents something plus something to the power of 1. A plus b to the power of 1. Well, these guys, they're just the coefficients. So what does the 1 here on the second line represent? Well, it represents the coefficient of a. It's going to be 1. And the other one is going to be the coefficient of b, like that. Okay?
Mm-hmm.
If you look at the third line, this is a plus b to the power of 2. So what does the 1 represent? Well, it represents the power of a, but now from this onwards, you have to be careful. It's always going to start off like this. 1, a, yeah? And then a to the maximum power. No b's. The next term will have the middle coefficient 2, and then the power of a goes down by 1, and then the power of b increases by 1, like that. And then the last term, it's going to be 1, b, and then 1 more power. So a's power goes down, and then b's power goes up. See that?
Mm-hmm.
Now let's build the third line. It's going to be, again, it's going to always end with 1 and 1 here. But now in the middle, we're going to have 1 plus 2, a 3. And then on the other side, you're also going to have 2 plus 1, a 3. So it's going to have 4 terms, right? Now look at this.
Mm-hmm.
If you want to open a plus b to the power of 3, start off with the first coefficient, 1. And then it's going to be a to the maximum power, in this case, 3. The next term will be the coefficient of 3 here from here. And then the power of a goes down by 1, so it becomes a squared. And then the power of b goes up by 1, so b. Can you tell me what the third term will be here?
3A.
3a what to the power of what? 1, right? What about b? What's the power of b? So a goes down, b goes up, right? So 2 became a1 here, b1 becomes b2 here, like that. Yeah?
Mm-hmm.
What's the last term? It's going to have a coefficient of 1, right?
And then B cubed.
Yeah, there we go. That's it. That's it. And then using this triangle, look at this. The fourth line, again, there's going to be 1 at the start, 1 at the end. What's the next number here?
4.
4. What about here?
The same.
6. Because 3 plus
Oh,
3. What about the next
okay.
number here?
It's a 4.
Yeah, it's a 4. There you go. And then you keep building this, right? 1, 1. Look at this. 1 plus 4, 5. 4 plus 6, 10. 6 plus 4, 10. 4 plus 1, 5. What goes here?
6.
What goes here?
15.
Here.
20.
What's the next number?
15, and 6.
There we go, right? And then you can keep going 1, 7, 21, 35, 35, 21, 7, 1. It's going to be symmetrical, right?
Mm-hmm.
So this guy that we just did down here, this is something plus something to the power of 7. So let's say we want to evaluate what a plus b to the power of 7 is. And it's pretty simple using this Pascal's triangle. No one is going to multiply these guys 7 times. The first term is going to be 1a7. The next term, look at the coefficient 7. It's going to be 7a6b1. What's the next term going to be? So the next coefficient is 21, right? So 21. The power of a goes down by 1, so it becomes a5. The power of b goes up by 1, becomes b2, like that.
Mm-hmm.
What's the next term?
35a to the power 4, and
Yeah,
then b cubed.
there we go, just like that. And the next one will be 35a3b4. The next one will be 21a squared b5 plus 7ab6. And then the last one is going to be 1b7. There we go. And if you count it, there should be 8 terms. 1, 2, 3, 4, 5, 6, 7, 8. Because it's always, the number of terms is always the power plus 1.
Mm-hmm.
Cool? It's a pretty neat little trick, right? Pascal's triangle. Anyways, why are we talking about this? Because this thing, you can't open the brackets. Okay, because it's to the power of a variable. You can only open the brackets if it is a whole number. Like x, if it was x plus y to the, I don't know, 3 halves or something, you're screwed. Can't open that bracket either. Anyways, so this one, we're gonna straight up plug and chug for a. X is x, so it's -2 to the power of n is -1 plus y is 3 to the -1. Everything to the power of -2 times n is -1. There we go. Now here you have to be careful. What is -2 to the power of -1? What does this guy evaluate to? Any ideas?
What do you do with a negative exponent?
We talked about this right earlier, like you toss it in the denominator. For example, a to the -1 is 1 over a to the +1. So you simply toss that -2 into the denominator, the exponent becomes a positive. Yeah?
Okay.
What
Mm-hmm.
about 3 to the power -1? What is that? Is it -3?
It's 1 over 3.
All right, do not make this mistake. I see this all the time, and I may have mentioned this before, but I'm going to keep mentioning it because this is a very, very common mistake. 3 to the power -1 is not -3. You don't know the amount of people, even in universities, that make this simple mistake, okay? That is not true. It's going to be 1 over 3. And then -2 times -1 is simply a +2. You can rewrite the inside bit as 1 over 3 minus 1 over 2 because that's the same thing. What's the common denominator between 3 and 2?
6.
6, right? So you multiply this by 2, this by 2, this by 3, this by 3. So you have 2 over 6 plus 3, or sorry, minus 2 over 6 minus 3 over 6 to the squared. And then you get -1 over 6 to the squared. What's -1 over 6 squared? I mean,
Is it
just
just 2 over 6?
nope, it is certainly not 2 over 6. That is out. Not even, that's not even close. Think about it this way. Whenever you have an exponent on the outside like this, you want to do the numerator squared. What's -1 squared?
Just 1?
And then individually, you want to do denominator squared. And there you go. That's the final answer. How does he get 2 over 6? 2 over 6 is if you do negative 1 over 6 times negative 2. Now this would be 2 over 6 if you multiply negative 2. But if you power it, do them individually. Okay?
Mm-hmm.
What is negative 2 over 3 squared? In a bracket, you have negative 2 over 3. What is this squared? Is it 4 over 6?
It's 4/9.
Yes. That is correct. Oh, there we go. Okay, now we're gonna get into a little bit more trickier things. You're probably just using numbers, but we're gonna use the letters and then we're gonna plug the numbers in. Look at this, x squared power n. What does that simplify to? Just the first guy here,
X to the power of 2n.
right? The second guy, you can't really touch it. The third guy, you can't really touch it. What is x to the 2n times x to the minus n? What does that simplify to?
X to the power of n.
That's correct. You have x to the power of n, and what do we do with negative exponents?
You put them under 1.
Yeah, toss it in the denominator like that, and this is it becomes a positive, and this is as far as you can simplify this. And now you plug the numbers in. X is negative 2, n is negative 1, y is 3, and then 2 times negative 1 is negative 2, like that. Yeah?
Mm-hmm.
Now what do you do? Just use the rule of flipping the numerators into denominators whenever you have a negative exponent. What we're going to do is we're going to toss this 3 to the negative 2 upstairs because it's going to become a positive. See that?
Mm-hmm.
Similarly, we're going to toss the negative to the negative 1. It's going to become negative to the positive 1 if you put it in the denominator like that. And now we're done. 3 squared is 9, negative 2 to the 1 is negative 2. Final answer. Was it tricky? I guess. What do you think of this?
It was okay.
So if you can do these guys, you can do anything they throw at you in school. Okay?
Mm-hmm.
Because we're using exponent laws, but we're also using like the variables, numbers, a bit of like everything, like a gumbo basically. Let's look at C. Is that openable? Like this bracket, can we open this bracket? We could not open this bracket. What about this one? It's a yes or no question, right? Here we're gonna do something. And you can do this as well. Okay, let's flip a coin, I guess. Heads. So that's saying it's openable. Do you agree? Or what if we
No.
flip it again? Why does it take so long? Okay, tails. So we got one heads, one tails. So it's a yes or a no. The answer is yes. You can't open a bracket if there's a sign plus, or when you're subtracting, you can't, or adding, you can't. But when you're multiplying them, you simply use the exponent double bracket rule. Like if you have a to the b to the c, this is a to the bc. This is openable, okay? And the trick is to just use one at a time. What's x to the n to the power of n? Like x to the n to the power of n, what would that be?
X to the power of n times n.
Okay, so what's n times n?
2n.
No, it's not. Try again. N times n is not 2n. N plus n would be 2n. What is n times n? What's 3 times 3? Is it 6? Because if you use this logic, if it was 2n, it would be 6, but we know it's not 6, it's a 9. N times n, Again, use the first law of exponents. It's n to the power of 1 times n to the power of 1. Whenever you're multiplying exponents, you add them like that. N times n is n squared, okay?
Okay.
So you would get x to the n squared. And then you do the same thing in the denominator. You'll get y to the n squared. Let me know if that made sense,
It does.
right? Because we're just simply just doing x to the n like that, and that's x to the n times n, and n times n is n squared like that. And now we can't really simplify this because we have different bases. By bases, I mean we have an x here, we have a y here. This is as far as we can go, and now we plug the numbers in. X is -2 to the power of n squared, so n is -1 squared. And on the bottom, you'll get y, which is 3 to the power of n squared, -1 squared, like that. So you get -2 to the power of 1, because -1 squared is a 1, and then 3 to the power of 1, which is a 3, and there you go. That's your final answer. Cool?
Mm-hmm.
All right, let's try doing D together. What would be the first step? What would you do? I guess there's multiple things you can do, but one of them is the best. No? You see this bracket in the denominator?
Do
This
you
guy?
open it?
That's gonna be the best thing to do. We're gonna open that. If you open that bracket, what do you get? Forget about the 2n on the outside. We're gonna clean from inside to outside, and we're gonna do this every single time. If you open that bracket on the bottom, what you get? Well, again, just do them individually, right? So you're gonna get x to the 2n and y to the 2n, like that. Do you agree?
Mm-hmm.
Now what do we do? What's the next step? Again, we need to clean the inside first. Forget about the 2n on the outside. This we'll deal with it last. They're like terms inside the bracket. No, nothing. Um, there's an x power 1 here, right?
Mm-hmm.
We're gonna move the 2n upstairs. You're gonna get x to the 1 minus 2n. If you move the y downstairs, what do you get on the bottom? So you move y to the n here with this guy. What do you get? It's the second rule of exponents. You subtract them, right? Like if you have a to the
Uh-huh.
3 over a to the 5, it's 1 over a to the 5 minus 3. It's 1 over a squared. You could also take the 5 upstairs, but then you would get a negative exponent, which is fine as long as you toss it in the denominator. So you can either take the 5 upstairs or bring the 3 downstairs. Bringing the 3 downstairs is better because it gives you a positive exponent. So if I bring the y to the n downstairs, what do I get? Well, you just get y to the 2n minus n, which is y to the n, right?
Mm-hmm.
Using this rule right here. Do you understand that? Because this is kind of a little bit important.
I
Right,
think so.
we can do like 20 of these, don't worry. That's the beauty about math. For example, you have y to the a plus 3b minus c or something weird. And then on the bottom, you have y to the 2a minus b squared plus z or something weird. Notice they have the same bases. Same basis means we can combine them, use the exponent laws. So we can either take the top to the bottom or bottom to the top. So if you take the top to the bottom, it's gonna become, you're just gonna be left with the one upstairs. And on the bottom, you'll have our original function, the denominator, and then you wanna subtract the exponent like this using the second rule. Okay?
Mm-hmm.
Same idea that we use here. Y to the n, if you move it downstairs, because these two, they have the same bases, you can combine the exponents and it's gonna become a minus. Here, try this. Y to the minus 3 over y to the 3. What is this equals to? Just bring the y negative 3 downstairs. What do you get? You'll get 1 over y to the power something.
Like if I bring the -3 down, does it become positive?
It does become positive, yes. It's gonna be y to the power something if you want, and then you're gonna combine them, right? Here's the steps. Y over 1 over y cubed times y cubed, because when you brought it down, it's going to be, the sign's gonna flip, yeah? And
Mm-hmm.
then see, notice they have the same basis, they're being multiplied, you add the exponents. So it's y6.
Okay.
What if instead of it being y to the -3, what if it was y to the 2? Now what do we get in the denominator? Y to the power of what?
To the power of 1.
Yeah, that's it. What if it was y to the power of n over y to the power of 2n? If you bring this down, what do you get?
Y to the power of n.
Yeah, that's it. So that's that. Let's go back to the question. Okay, so we have a bunch of things. You could throw the 2n in there, I guess, but it's gonna give you a squared. We'll just leave it outside. Or actually, what's 1 minus 2n times 2n?
Does the 2n apply to everything?
It does.
2n minus 4n.
It's not 4n, try again. You're not adding them. It'd be 4n if you added them. You're multiplying them. What's 2n times 2n?
2n to the power of 2.
4n to the power of 2, right? 2n times 2n. Multiply the number with the number. 2 times 2 is a 4. Multiply the letter with the letter. N times n is n squared, not 2n, okay? N times n is n squared. That's why you get 4n squared. And on the bottom, you'll get y to the power of n times 2n. What's n times 2n?
Is it just 3n?
You're not adding them. Try again. N plus 2n would be 3n. You're multiplying them. It is not 3n. You can look at it like this. 1 times 2 is a 2. You multiply the number with the number. What's n times n?
N squared.
Yeah, so you'll get y to the 2n squared on the bottom, like this. Cool?
Mm-hmm.
And that's as far as you can go. And from here, you can just plug the numbers in and do this. The hardest part is getting to this. So starting from here, getting to there. That's the hardest part. Okay, let's try doing these guys. I know it looks a little bit intimidating, but it's not that bad. Like I said, there's only 3 rules. As long as you know how to apply them, you should be fine. Right? That's the idea. As long as you know how to apply the rules, you should be fine. Look at this. We have a double bracket rule. This is a third rule, double powers. What is this going to be? It's going to be x to the power of something. Open that bracket. And it's this rule.
Is it x to the power of 10 minus 2r?
Yeah, that's it. That's all there is. Okay, like that. That's the final answer for this. But I can show you how this works. What you can do is you can deconstruct this. Doesn't apply to this question, but the idea is important, I guess. And you're gonna need to deconstruct it sometimes. And this thing, we use it everywhere, okay? I'll show you like a quick example of this exact idea being used in a high-level math course. But to deconstruct this, what we do is we're gonna do x to the power of 10 times x to the power of negative 2r. See that? We're reverse engineering this. And then that's a negative exponent. So what you can do is you can toss it in the denominator. All of these guys are equivalent. This is the same thing as this, same thing as this, same thing as this. See that?
Mm-hmm.
Do you understand what happened from here to here?
Yes.
Because if you add them up, x to the 10 times x to the negative 2r, they're being multiplied, so you add the exponents, and you'll get 10 minus 2r, right? Like that.
Mm-hmm.
Let me try and show you. I'm trying to think where this could be, because I had to use this exact same thing. Actually, no, let's freak you out. So I was gonna show you the small version, but let me see. A nice deconstruction. You see, look at this, the quadratic things that we were doing, right? Look at this. Man method,
Mm-hmm.
important. Basics are important as well, right? Um, don't worry about all these symbols. You will be doing something like this in university if you ever pick a science-based course. Look at this right here. We're using the exponent, right? We have 101, and then we're multiplying this with 100 or something, and then you add the exponents up. Applies to pretty much everything we do here has a purpose when you eventually do some other type of maths, okay?
Mm-hmm.
See the quadratic, oh, and here's another cool thing. Completing the square, you remember doing this? Completing the square, writing it in the vertex form, boom, right there. Every little math thing that we do applies. That's pretty much it, I guess. Yeah. You wanna know what this is about? Laplace transform is, it's kind of hard to explain it, but I'm gonna try it. So like the whole point of math is like, why are we doing this, right? What's the real life application of this? Um, so what it gives you, okay, what it gives you is, think of it like this. You have a curve, yeah? See this? On the x-axis, we have time. On the y-axis, it's any y variable, doesn't matter. Could be like concentration, could be like light intensity, doesn't matter, yeah?
Mm-hmm.
You get this in kind of like a two-dimensional thing, right? Two-dimensional thing. What the transform, that transform, what it gives you is it's gonna turn this two-dimensional figure into like a three-dimensional figure. And in a 3D figure, there's we've only seen x and y axis, right? There's something called a z axis. And it kind of flips though, like it's weird. So the x-axis from 2D becomes the y-axis in 3D. The x-axis in 3D is right here, actually, along the diagonal. And the vertical axis becomes the z-axis. Anyways, once you transform this in 3D, very difficult to draw, but it's gonna look something like this. And I don't know if you understand this, but this is it's a three-dimensional figure. So it's like a thickness to it. So like there's the exact same replication behind it, exact same replication behind it, like that. And it kind of becomes like a plane. So that's the point. We're transforming a two-dimensional diagram into a three-dimensional diagram. Where is this used in real life? It is used in thermodynamics.
What's that?
This is the science behind heat.
Oh, okay.
That's one of its real life applications. You will see this in grade 11, or yeah, grade 11 chemistry. You'll see this, maybe even in physics. That's where it starts. But then it gets more difficult if you take a course like this in university. Anyways, that's the real life application of that, right? So we're using these small concepts, something like simple as this. These are the basics, these are the building blocks. We're going to use these concepts in other math, and then we're going to use this results and apply them in real life. So everything that we do has a purpose, right? The sine cosine things that we're doing, very, very popular, has a lot of applications, a lot in real life, everyday life. Like how we are talking on Zoom, you bet this has something to do with it. These the math that we do, has something to do with the creation of the entire platform or the software, everything. So that would be the final deconstructed answer. But for this question, we want to write it as a single exponent. That's the final answer. Let's look at D.
Okay.
The goal, again, this is the purpose. We're going to write it in terms of x to the power something. What's the first step?
You open the bracket.
Right, you open the brackets. So what do you get if you open the brackets?
X to the power of 21 minus 3r.
Great, now let's combine these two x's. What do you get? Use the first law. Which says if you have xa times xb, it's xa plus b. Combine the bases.
Do you get 3r squared?
No, you do not get 3r squared. So combining the bases, right? Because we're not doing x to the 21 minus 3r to the power of r. Then yeah, you'll get negative 3r squared. But we're not doing that. What we're doing is, look at this, it's the first law. You have the same base with different exponents. You add up the exponents like this. Where this thing is your a, right? If you want to use that formula, that thing is your a and this thing is your b. And what does it say? X times a times xb is a plus b, so 21 minus 3r plus r. And you would get x to the 21 minus 2r as the final answer. If you want to deconstruct this, you got to split them apart. It's going to become x to 21 times x to the negative 2r, and you can toss this in the denominator. And sometimes it's, well, doesn't apply to this, but it's better to deconstruct it as well. Like, for example, yeah, I'll show you what's the point of deconstructing this, right? Because usually, right, usually this x is gonna be a number. So what you can do is you can pull it out all the way out. You can take it out, and then you're left with 1 over x to the 2r inside, right? Let's say this is some function, yeah?
Mm-hmm.
R is the independent variable. You pull the constant out, it's easier to work with. Um, Anyways, that's the final answer. Let's go off on a quick tangent here. How does this work? It works like this. We don't care what it looks like, okay? We don't care what it looks like. I'm gonna tell you a couple of things. We've done slopes, right?
Mm-hmm.
Like this slope is mx plus b. I don't know if we've done slopes for quadratics. What's the slope of x squared? It's a trick question. What is the slope of y equals x squared? The diagram is right here. This is y equals x squared. Well, it's like x squared minus 2, but same thing. What do you think? Well, the short answer is that it doesn't have a single slope. Like if you look at this point, it has a slope going upstairs or sloping upwards. If you look at it here on the vertex, the slope is 0 because it's a horizontal line. If you look at it here, the slope is this way, right? So the slope of y equals x squared depends on the x value. Unlike a linear function, the slope is always going to be m regardless of what the x value or the y value is. The slope is always constant. But for polynomials, higher degree functions, the slope is dependent. It changes. It varies. The slope varies from one to the other depending on what the x value is. Why are we talking about this? Because there's another concept which we haven't really done, and which is the idea of the area that's underneath the curve. You see, for a linear function, it's simple. Because if you want to find the area, let's say, um, this is some linear function. It starts here at -1, and let's say it ends here at 3. Okay, we're interested in finding this area. Let's say this is 2. How do we find this area here? Notice it's just a triangle. What's the area of a triangle? Are you saying something? I can't hear you. You're muted.
Oh, it's base times height over 2.
What's the base here?
3.
No, it's not. Try again. Does it look like it's 3? The base is the length of the base.
It's 4.
What's the height?
2.
And divided by 2, right? Base times height divided by 2. 2 and 2 cancels out. The area is 4. It's easy
Mm-hmm.
for a linear function. Now, what if I flip the switch and make things more difficult? What's the area from here to here? Let's say -1 to 1. And you can say this is 3. What's this area? What's the area of a circle?
Pi r squared.
Does that look like half a circle?
Mm-hmm.
Yeah, it does look like one, but it is not half a circle. So we
Oh.
can just do we can't just say the area of that is half the circle, like pi r squared over 2. We could do this if we knew it was a circle for short, but this is a quadratic function. It's not a circle, even though it looks round. So now things become very difficult, right? We're trying to find the area there, but it's not a circle, and we can't just use triangles or any of the shapes. So I'll just tell you what it is, but you'll see this later. To find the area of the circle, you need to use a method called integration. and that gives you the area of a circle. The symbol looks something like this. We're trying to find the area from -1 to 1 of x squared, and then you want to put dx here. So use this. Don't worry about how this works. The answer is going to be x cubed over 3 from 1 to -1. The answer is going to be 1 over 3 plus 1 over 3, 2 over 3. So the area of this is 2 over 3. You can't use shapes. Basically, the point is you can't use shapes to find the area of any function apart unless it's a linear function. Same thing applies to like exponential functions as well. Like what's the area from here to here? You need to use something called integration, which is looks like this. Okay?
Mm-hmm.
Interesting?
A little.
You'll see everything we ever talk about, you will eventually see it. Well, I guess as long as you are in school, I guess. Do you have an idea of what you want to do eventually in like college?
Not really.
It's okay, but eventually you're gonna have to figure it out. Like you still have a couple of years left though, right? Around maybe grade 11 is when you kind of need to, yeah, because you have to apply for programs. Don't know how it works in that province, but in this province, I think you can only apply to 3 colleges. Yeah. Anyways, let's look at this. I'm gonna rewrite it in this form because just cause. How do we solve this? We want to write it in terms of b to the power something. No?
Do you just subtract?
Yeah, you just subtract. You can either subtract top to bottom or bottom to top. I'm just gonna move this guy upstairs. So it's gonna become a 2m plus 3m minus m minus n. And don't forget, whenever you're subtracting, make sure you put a bracket in the second term. Okay?
Mm-hmm.
Make sure you put a bracket on the second term or whichever is being subtracted. And when you open the sign, when you open that bracket, the sign is gonna flip. Oh, 2m plus 3m is just 5m. So first guy is just 5m. And then minus m plus n. Do you understand how this sign became a plus n, even though we started with a minus n here? Because of the double negatives, we're subtracting a negative number, becomes a positive.
Mm-hmm.
Then you have b to the 4m plus n, 1n, done. Okay,
Okay.
not that difficult, right? The math itself is very simple, actually. Like this is just like grade 7, 6 level math. By math, I mean just like adding 2m plus m. What is this? Like the math is simple, or subtracting it. The difficult part is the logic behind it. Same idea. We need to write this in terms of a to the power something, one number allowed only. What do we do? No? No ideas? Look at it. There's an a here, but we have 1 over a here. I want to rewrite the second guy as a to the power of something. What does it become? What's 1 over a in terms of a to the power of something?
A to the power of -1.
Right, that's it, right? That's it. So you have a to the power -1. What's -1 times p? It's a to the power negative p, right? If you open this bracket,
Mm-hmm.
you'll get a to the power negative p. Now what do? We want to combine the bases. Any ideas?
You add.
You add. What's 10 minus p minus p?
It's just a to the power of 10.
So it's 10 minus p plus negative p, yeah? The p's don't cancel out.
Oh, so it's p squared?
No, it's not. Try again. P squared, if it was p times p is p squared, not p. So we're doing negative p minus p. What's that? Negative p minus p.
You get 2p?
Yeah, that's it. There you go. The power only increases if you're multiplying. Keep that in mind. You see, it's never going to be
Mm-hmm.
p squared. It's only going to go up if you multiply. If you're adding or subtracting, the power is going to stay exactly the same. Let's try this one. And I know it looks daunting, but it's not that difficult. Step 1, we have x's. I want to write this as x. What do I get? If I want to write the second guy as x, it's 1 over x right now. Same thing we did last time.
X to the power of -1 to the
Yes,
power of n.
yeah, and that just becomes x to the power negative n, m, right?
Mm-hmm.
Here's another question. Can you open this bracket?
Yes.
Yes, you can. What if it was 3 plus x4 to the power of that? Can you open this bracket?
Yes.
No, you can't. Pascal's triangle doesn't allow variables or non-integer numbers. This one, you can't open it. This one is good. When you're adding, subtracting, if you have a variable in the exponent, you can't open it. But if you're multiplying, dividing, doesn't matter what's in the exponent. So this one, you can open the brackets. If you open the brackets, the 6 minus m applies to every element inside the bracket. Okay, so it's going to be 3 to the power 6 minus m times x to the power of 4. But the 6 minus m also applies to this guy like that. See that?
Mm-hmm.
This one will be a constant, so you can't do anything with this. What about these two? If we combine them, what do we get? 'Well, first open this bracket. If you open this bracket, what would you get? X to the power what? We're just opening this bracket here.
24 minus 4m.
Yes, and now if you combine these two, what do you get? The two x's. They have the same base, we're gonna combine it as 1.
24 minus 5m.
That's it, final answer, 1 and done, okay? Was that difficult?
Mm-hmm. No.
Math itself is very simple. We're just adding and subtracting or multiplying and dividing, right? We're just doing 4 basic operations. The tricky part is using the rules properly. Anyways, let's call it a day there.
All right. Thank you.
See ya.